Welcome to a lesson with Dr. Powell. Let's take a look at how we can take a recursive sequence and turn it into an equation like this, which is not recursive, meaning it doesn't depend on a previous entry. This is just a function of n now for where we are in the sequence. And the sequence we begin with is this one right here, and this is a naught. So at the beginning, 1 and 3, and then this is how to go from to the next entry from the previous two entries. Okay, now in the process, as we go along here, we're going to see a way that how we can find an nth power without using the same ideas as we've had before, but without actually having to do any kind of division or generalized division or anything, but using another technique via system of equations that actually gets us quickly to what we want for the nth power. Now, first, how do we write our recursive sequence in a formula with a sub n with a matrix power? Well, we can think of a function like this, where you take in an and n plus 1, and you output an plus 1 and an plus 2. So two entries, and then the next, and then you just kind of shift in your sequence forward by 1, and you're looking at the two entries there, just shifted 1 forward. So the last entry, n plus 1, in this pair becomes the first entry in the next pair. So if you look at a function like this, thinking of like x and y, x being an and y being an plus 1, you could signify what's happening by this. How did I get the 2x plus y? That's simply the 2an plus 1, because I'm thinking of x as being an and y as being an plus 1. So we can effectively get this function. Now this function, as a matrix description, which we can get by with the column interpretation by the destination of E1 and the destination of E2. So E1 is like 1, 0. Where does it go? So meaning like when x is 1 and y is 0. X is 1 and y is 0, you're going to get 0, 2. E2, that's like 0, 1. So when x is 0 and y is 1, x is 0, y is 1, that's 1, 1. So we get a nice matrix which describes this process. And this is the matrix we'll be working with. Okay, now think about where we start. 1, 3. Every time we multiply by this matrix, it shifts us one more place forward and forward. Okay, so this starts out as a 0. Well, if we shifted it n times, then the result of this product right here, if we just look at this product right here, the result of this product will actually end up being a sub n, because we moved from a sub 0, a sub n, and then next go an plus 1. But we want to pick out only the top guy. How do you pick it out? By picking out the first row. How do you pick out a first row? Row interpretation, 1, 0 picks out the first row. So we put a 1, 0 here, this row matrix in the front to pick out a sub n. All right, now, now we have a sub n written as a formula with a matrix power in it, raised to the nth power. Let's see how we can write this nth power as to get a nice formula for it using the technique of polynomial division. However, we're gonna catch the remainder without doing any division at all. So first, we need to find the characteristic polynomial of this matrix. Doing so, we think of a 0 matrix, which is that we would get if that have a 0 column action, that is. So 0 column action matrix. If this matrix considered as x itself, so if x was considered to act as this matrix does. So a 0 action matrix would be this one, because x is down the diagonal, right? Subtract that matrix would be like 0, because we're assuming those actions are the same. So, and as mentioned previously, even though the connection is actually non-trivial, because the entries of the 0 matrix are different than the entries of this one. So it does take a little work to show, but we're taking for granted that the determinant of this 0 acting matrix behaves like 0. So determinant of this is x squared minus x minus 2 if we work it out, and we can factor it like this. Okay, so if we want to divide x to the n by this characteristic polynomial, we can kind of think x to the n is going to be equal to the divisor here times a quotient plus a remainder. Now, what happens if we plug in -1 into this whole equation just for x, all right? Then what happens to this part? This will turn into 0, right? So this whole part is gone. That's really nice for figuring out what's going to be in the remainder. We know the remainder is going to take on the form ax plus b, and yes, this a is referring to two different things, the sequence and there, but we'll just say without the subscript, we'll just keep it distinct and just say it's a number over here, even though technically speaking, the letter A would refer to the sequence, but I'm not going to do that here. We're just going to use this A will be something different. So ax plus b right here is going to represent the remainder because the remainder has degree 1 at most, at least. And that's because the characteristic polynomial has degree 2 and the remainder will have degree less. So we know it's of the form ax plus b, right? So if we plug a -1 to this whole line, we'd have -1 to the n is equal to a times -1 plus b, which looks like this. -1 to the n is equal to -a plus b. If we plugged in 2, this part will go away again. We have 2 to the n is equal to a times 2 plus b. So we have a nice system of equations. A little air dropping with a -1 times this row upward. So upward would yield, so the b's would cancel, and we'd right here we would be left with 3a is equal to 2 to the n minus -1 to the n, just like that. We can solve for a, so we have a, and then knowing that b would just be, put the just add a to both sides in here, so just a plus -1 to the n. We have what a and b are. Okay, now we're pretty much ready. We just got to throw everything into this formula and see where we're at. Let's think about this. So what we have so far, let's think about 1, 0 multiplied to as a row multiplied to our matrix raised to the nth power. So notice we're just going to put 1, 3 off to the side for now and just kind of think about what's here. Think of the row matrix 1, 0, and let's now write this power as what we have it. So a times the matrix plus b times the identity matrix, or like a scale, b acting as a scalar with b's down the diagonal. Okay, so this right here is another description for this if we using the a that we found and using the b that we found. Now, think about what this does. This picks out the first row, and as you can distribute it in, so to pick out the first row of this matrix, the first row of that matrix. So picking out the first row of this one is 0a, picking out the first row of the next one is b0. So add them together, just get matrix BA. And that's what we'll be taking BA and multiplying it to the column 1, 3. And that's just a dot product. We have b plus 3a. So b plus 3a will represent the formula for a sub n. Then we just plug in what we found for each of these. For a, we found this, and then b, remember, it was just a plus -1 to the n. And we can double check this if we want to, at least for one of the positions. This formula works well and holds, at least when n is greater than or equal to 2, so beyond the 0 and the 1 positions. Okay, so what about at the 2 position? If you plug in 2, you have, this is 1, and then right here you have, so this becomes -1 because -1 squared is positive, so minus +1, and then you have a 4 minus, so 3 over 3 is 1. Okay, that's the same thing, that's also 1. So you have 1 plus 1 plus 3, which is 5. Now, if you notice, if we go back here, if we plug in a sub 0 is 1 and 3 right there, you have 2 plus 3, which is 5. It works, at least in the first place. We can easily check that. And what we have is we have a nice formula that is not recursive. You could simplify this by you can combine some things, add fractions, whatever. But this is the formula, and we have used our method. Thanks for watching.